Okay, let me just log on. I'll start with camera, but I want to log on so you can launch your program. Oh, thanks. Okay, guys, I'm not asking any questions because we are doing revision today. So it's you who should be asking questions. Please feel free to ask as many as you wish. Just before we start, let's start with something a bit more relaxing. So on Friday, we were checking the acoustics of the theater. By the way, I'm surprised. I expect everyone to be there. There's so many free chairs. And we established last week that that is the best place to learn linear systems, that side over there. However, the group that was in the middle, we gave them 0.5 because we thought there was nothing here. But actually, if you look, if you zoom in, okay, they actually did something here. Where is it? Okay. They did something here, and there is a graph here. Okay. I lost it now. Okay, here it is. Okay. So I'm happy to correct the mark, the original mark. But just a lesson for all of you, if your exam is done with invisible ink, don't be surprised that you don't get marks. Okay, zoom out. Okay, so I'll change this to 5, because the graph is still wrong. It's just there. Oh, it wouldn't zoom out now. Okay. Okay. So that much about the last week's exercise, introduction. Where is it? Now, this is the paper from, 5 years ago. So as you see, things don't change very much, very dramatically. I explained briefly what is the approach here. It is effectively the same system as what you had in your test one, apart from in test one, of course, you didn't have the block diagram because you didn't know anything about the block diagram. So we explained that, how you complete this block diagram. Then we went on to do this question 2, which consisted of 3 completely independent parts. Part A was about identifying the system from the unit step response shown in this graph. So what we did, if I still have those calculations from Friday. Okay. So we estimated the peak value, the steady state value, and therefore the percentage overshoot. We also estimated the time to the first peak. Based on that, so based on the percentage overshoot, we used the equation provided. The equation provided somewhere here. The formula for the percentage overshoot is here. So we use this equation, knowing the value of the percentage overshoot to be 10. We use that to find the damping ratio, because there are no other unknowns here. So when I did, I actually made a mistake, or actually copied the wrong solution. So I made a mistake 5 years ago, and I didn't correct it. So this number, 0.35, is actually psi squared, and not psi. So when you find the square root of 0.35, you get 0.59. So almost 0.6. So that was pointed out to me by few of you here after class, because this is actually the part I like, because they said you got settling time to be 26.6 seconds. And if you look at the graph here, settling time must be much less than 26 seconds. That's actually good thinking. I like that. You think about the results you get, or someone else gets, in this case. So when I checked, obviously, I realized I didn't find the square root of 0.35. When you correct that, then in the equation for peak time, we found that to be 8 seconds. Therefore, finding omega, again, it's not 0.35 squared. It is only 0.35. So you get different value for omega n as well. So finally, settling time is 3.91 over omega n psi. So both of these values need to be corrected, and you get about half of the value for the settling time, 13.6 seconds. Okay. But that's only calculations. That happens. That happens to humans. Humans also lose marks, so be careful. Humans also make mistakes when marking, so you get more than what you deserve. If you get less, obviously you'll complain and you'll get that corrected, like those guys from the Friday group. I'm apologizing. They didn't complain. I just noticed later on. Okay, so this was part A. Any questions on this? Part A of question 2 from the past paper. Part B is purely inverse Laplace transform using partial fraction method. Okay, so the question says, using, by means of partial fractions or otherwise, find the inverse Laplace transform of this function. Okay. Someone also asked me during the tutorial on Friday, what do you mean by otherwise? Well, there are clearly other ways, apart from partial fractions. I'm not sure that those ways are any shorter. Okay. But partial fractions, you should know. We did so many examples on partial fractions. If you know If you can think of another way and you think it's easier, go for it because it is said or otherwise. Okay, so question 2, part B. Part B, so we have f of s equals to 1 over s squared, s plus omega squared. Maybe I should show you one of the otherwise methods of solving this. If you say that f1 of s is 1 over s plus omega squared, then you can find f1 of time, which is inverse Laplace of f1 of s. You see the difference? I don't have square here. So I removed 1 over s temporarily. This case should, if I remember right, should exist in the tables. Okay, here it is, case 18, s brackets s plus a squared. Don't be misled by omega. Omega is a. Oops. So omega is a. So don't go down here looking for s squared plus omega squared. This would be wrong. It's s plus omega squared. So it's this. So you find this to be equal to 1 over a squared, or in our case, omega squared, brackets 1 minus e to the minus at minus at e to the minus at. F2, sorry, not f of t, which is inverse Laplace of f of s, now can be found as the integral from 0 to t of 1 over omega squared 1 minus e to the minus at minus at e to the minus at dt. Yes? Sorry, I keep, yeah, okay, I keep mixing them. So this is not a, this is omega, this is not a, this is omega. This is also not a, this is omega. Thank you. Omega, omega, omega. There you are. Thank you. That's otherwise. Now, if you think solving this integral, well, solving this term is easy, solving this term is easy, this one will require a little bit of work. So I'll leave that to you to decide whether you want to do it this way. I'll just show you the beginning of the partial fractions method. Partial fractions for the same problem. You need to express f of s as a sum of much less complex fractions, therefore named partial fractions. There are two correct ways of doing it, and there are many incorrect ways, obviously, but there is one very popular incorrect way, so I will point out that. So correct way, one of the correct ways is to go like this. So you can see the function. This root s is repeated twice. So we have a over s plus b over s squared. This root here is also repeated twice. So you then go c s plus omega plus d s plus omega squared. This is correct. Or the other option, which is also correct, is to go like this. S squared is effectively a second-order polynomial. So we have to put a first-order polynomial in the numerator. But that's effectively the same as these two, okay? And then plus, again, second-order denominator, first-order numerator, CS plus D. This is also correct. What often happens is this. F of S equals A over S plus BS plus C over S squared plus D over S plus omega and plus ES plus F over S plus omega squared. And this is, I'll use slightly different color here. This is wrong. Okay, because effectively you're combining two methods. I mean, effectively what will happen is that you will have 6 unknowns and only 4 equations. So you won't be able to solve to find A, B, C, D, E, and F. Yeah. So to check whether you're starting the right way is to see the order of the polynomial, which is 4, and how many variables or how many unknowns you are looking for, which is 4, or 4 over here. Okay, but I'm not going through the whole procedure because I have different plans for today. Sorry, just any questions on part B? Okay, that's good. Part C is simply not going to be in the test because part C requires lecture 10, steady state errors. That's exactly the title of lecture 10. So back then we had an old system, so the mid-semester test would come after lecture 10. We changed that in the meantime, so don't worry about part C. Simply, you know, you may be able to solve it, but that's because you're hardworking and going ahead of me. Okay, so don't worry about that. Now, the plan for today, I already instructed your demonstrators to start set 7 of past exam questions from the beginning. Set 7, also known as past exam questions. So it is this one. Okay? So I believe they're already working. They have already started doing problems 1, 2, 3. I don't know how far they're going to get. I will start from the back, doing 10, 9, 8, and see how far I get today. So hopefully we will overlap somewhere in the middle. Okay. If we don't, then it's up to you to practice those problems in the middle. So I'm doing now problem number 10. Okay. So problem 10 deals with a nice and simple system used for loading coal onto a truck or train or truck. It could be a truck as well. So you have a wagon here on a weighing platform. Coal is being, so this is a conveyor belt bringing the coal into the wagon. So it's a real life system, real engineering problem. Instead of reading the whole text, I'm going to describe it quicker. And, well, we refer to the parts of the text later on when necessary. So here's the empty truck or empty wagon. We are loading the coal. This weighing platform has a spring underneath, a viscous damper underneath, and the load cell. So as you load, as the weight increases, the platform moves down. The displacement is sensed by the load cell and converted into voltage. The voltage generates current, obviously. So the voltage between these two lines generates current that goes through, well, first it goes through the amplifier, then through the resistor, then to the inductive coil. Inductive coil generates an electromagnetic force which pulls the pointer. So the pointer is telling us how much coil we have in here. Pointer is also, so the movement of the pointer is balanced by this spring over here. Okay. So this switch doesn't actually do very much for the system, doesn't affect the workings of the system. In reality, when a certain weight is reached, then this switch will stop the conveyor belt until the next truck comes on the platform, then it keeps loading again. So it is a kind of automated system. But this part is irrelevant for our problem. Okay, we'll see why. Okay, so at the beginning of loading, when any coil mass loaded is much smaller than mass m, otherwise negligible, form dynamic equation relating now different things. Dynamic equations, so that's only time domain, only equations, only differential equations. Relating the cumulative load W in kilograms to the deflection X. Okay, so how is this platform going to move as a result of the loading input, W? Okay, let's see. So question 10, part 1, subpart A. If this is our platform with mass m, we have a force in the form of the weight of the loaded coil. So it's Wg, because W is in kilograms, so it's mass. Cumulative coil input is mass of the coil, and the force is mass times G. We have the spring resisting the displacement, and we have the damper resisting the displacement. This force here in the spring is K1x. Okay, we didn't say that the displacement of the platform is x. It's K1x. It's not x minus y, or it's not x1 minus x2, because the other end of the spring is fixed. So if you call this displacement y, it will be 0 anyway. So it's just x. This force in the viscous damper is proportional to the relative velocity. So it will be c x dot. Again, the other end, where is it? The other end of the viscous damper is also fixed. This displacement is 0. Load cell, if you check the text, load cell has no effect on the movement of the spring, of the platform. It's just there to sense the displacement, but doesn't generate any forces to resist the movement of the platform. The load cell LC has a critical, and does not interfere in any way with the spring damper mechanism of the platform. So just there, sitting there and measuring displacement, not generating any forces. Okay, from here, we can write the differential equation that Wg minus K1x and minus Cx dot equals to mx double dot. The sum of all forces equals to inertia. Or we can rewrite it as Wg equals mx double dot plus cx dot plus k1x. Okay. That's all they're asking at this stage. Part B. We need to relate the deflection of the load cell to voltage VI. VI is here. Okay, so somewhere in the text it says again, the load cell LC has a characteristic mu in volts per meter. Okay, so X equals to mu times what? Sorry, wrong way around. Voltage VI equals mu X. Okay? If you're not sure, check the units once again. Mu has volts per meter, X is meters, so you end up with volts. Times, yeah, times, I was just about to finish the sentence. But you are correct, you are correct. So this voltage VI mu X is the voltage here. After the amplifier, it is times A. Okay. That's it. That is the differential equation. Zero order differential equation. There are no differentials. Okay. Part C. Everyone happy so far? Part C. Relate voltage to current. Okay. Now, voltage VI. So voltage here will be equal to voltage across the resistor plus voltage across the inductor. So VI. And obviously, there is a current going through this circuit here. So VI will be equal to R times I plus L di by dt. Done. Part D, relate current I to deflection Y. Okay? So we have to see somewhere here that current I generates a force. So now we have our pointer being pulled by, how do we call it? Electromagnetic force to one direction and pulled by this second spring here. So it's K2 times Y. I think they say also that the mass is negligible. The pointer is very light, obviously compared with the, with the truck on the platform. Yeah, it says somewhere here. I'm pretty sure it says that. Okay. So, F electromagnetic force is equal to Fi. Okay, so Fi. So let's be consistent. So it is Fi. Fi is proportional to the current via coefficient alpha. So Fi is also equal to I alpha. So I alpha or alpha I equals K to Y. Okay. So that will be part one answered. Everyone okay so far? Part 2, translate the system equations into transfer functions, x over w, vi over x, I over vi, and y over I. So effectively use these four equations, four differential equations, to create transfer functions. That's what you need to do. So part 2. B. X of s over w of s is obtained when you apply a Laplace transform on this equation. So Laplace transform will give us g w of s equals to ms squared plus c s plus k1 times x of s. So the transfer function is now g over ms squared plus cs plus k1. Okay. Now, next one is vi over x of s of s. Which is equal, when you look here, w over, I mean, you obviously can apply Laplace transform. All you're going to get is vi of s equals mu a x of s. So vi over x equals mu a. Next thing is I of s over vi of s. Again, from here, Laplace transform gives us vi of s equals r plus ls I of s. So I over v will be equal to 1 over r plus ls. And finally, from this one, Laplace transform, because we are looking for y of s over I of s. So over here, you get very simply alpha I of s equals k2 capital Y of s. Y over I will give us alpha over k2. Sorry, we are still going to need this. Okay, so far so good. No drama. Part 3. Obtain the transfer function. Part 3. Obtain the transfer function y of s over w of s relating pointer deflection to the call input, because that's really what interests us. So y of s over w of s. Here you have two options, two correct options. One is long and tedious. The other one is very simple and straightforward. The long and tedious way is to get back to these differential equations, these four differential equations. Eliminate all intermediate variables that you don't need. Okay, you don't need x, you don't need vi, you don't need I. All you need is w, the input, and y, displacement of the pointer. That is, as I said, long and tedious because you have some differentials here, and so it's a long process, but it would be correct. It is acceptable. Or, since you already have these 4 individual transfer functions, what you can do is write the following. That y over w is equal to y over I of s times I of s over vi of s times vi of s over x of s and times x of s over w of s. Okay. This is correct, obviously, because if you cancel these, you end up with y and w. But I'm not canceling anything. I'm just going to use the expressions I already have for these 4. We just derived them. Okay. So our transfer function is now, okay, let's do it this way. G ms squared plus cs plus k 1 times mu a times 1 over r plus ls times alpha over k 2. So the whole transfer function is g mu a alpha over k2 ms squared plus cs plus k1 r plus ls. Okay, my advice to you is, at this point, don't rush and multiply these 2 polynomials. Leave the denominator factorized for as long as you can, because the factorized form is usually much more needed later on than expanded form. So leave it as this. This is your answer, after all. If you expand, it is still your answer, but then later on you may struggle to answer other questions, because you will need, maybe you will need to factorize it again. Okay. Everyone happy here? If I'm moving too slow, please give me a sign or something. Start yawning or start leaving. Okay. Part 4. Now you have numerical values. Find the time constants associated with the weighing platform and the electrical circuit, and show that they are 1 second and 0.1 second, respectively. Okay. So we need to find the values of the time constants. So here you see why it is wise not to factorize the denominator, because you still have your mechanical part separated from the electrical part. Okay. Apart from, to find the time constants, you need to write the normalized form of the transfer function. No, to write the non-dimensional form. So you need to get m and l outside. So it is g mu a alpha over k2 m l, and then in brackets s squared. I'm still writing a normalized form, aren't I? Okay. S squared, we will see. Cms plus k1 over m. And here it is r over l plus s. Okay. We can still work. We can work even with the normalized form and get the time constants. Okay, let's substitute the values here. So r over l was the units. R is 10, L is 100 millihenries. So R over L is 10 over, I just said it, H is 100, okay, 100 milli, so it's 10 to the power minus 3 if you want an SI unit. Okay, so it is 10 over 0.1, which is 100. But that's R over L. Time constant, tau, is L over R. Do you all agree with this? No one is saying anything. Because I did the normalized form. Normalized form doesn't give me the time constant straight away. The non-dimensional form, no, I don't have a, so this will be equal to, non-dimensional form will give me this. G mu A alpha, yes, over K2 over K1 R, brackets, M over K1, that's not right, it's K1 R. M1 over K1 S squared plus C over K1 S plus 1 for non-dimensional. And here we have 1 plus L over R S. Okay. This is non-dimensional, so this is the time constant. L over R. But this is reciprocal to this coefficient here I have in the normalized form. Okay, so yes? That there is no small m. There is capital M here, and there is small mu here. Mu has a long tail over here, okay, whereas M should have much sharper corners than what I'm showing here. But the legs should be of the same length, whereas mu has one leg much longer than the other. Sorry, why? How do I know that this is the time constant? Because, first of all, I have 1 here and 1 here. So the coefficient with s to the power of 0 is 1. That is the definition of non-dimensional form. When you have a non-dimensional form, you read what multiplies s. That is the time constant. It's very simple with the first-order system. We'll see about the second-order system in a moment. But with the first-order system, what multiplies s is the time constant. Here, what multiplies s squared is the product of two time constants. So let's see how we deal with this one. As long as we agree that tau electrical is now L over R, which is 0.01 seconds. Okay. Let's just do this before the break. Tau mechanical. If we substitute the values, well, either here or here for the mechanical part, we are going to get, now I'm checking my calculations over here, s squared plus 400, because C, let's check the values here. C is not 400, 4,000. Everything here is SI, so nothing to worry about. Over M, mass is 2 tons, so it's 2 times 10 to the power 3. 2 tons, convert into kilograms. And plus K1, newtons per meter, so we just copy the number. 2,000 over 2 times 10 to the power of 3. This is now equal S squared. 4 over 2 is 2 plus 2S. 2,000 over 2,000 is 1. Which is equal to S plus 1 squared. At this point, our life becomes much easier because although we have 2 time constants, they are the same. They are the same because, do I really have to write this? This is equal to S plus 1, S plus 1. So we have 2 time constants. This is 1, this is 1. So what multiplies S is the time constant. What multiplies S here is the time constant. So you have 2 time constants, but they are the same, and they are equal to 1 second. So this is mechanical part. Tau mechanical is 1 second. Okay. So the weighing platform and the electrical circuit, the time constants are 1 second and 0.01 second respectively. So we have proved that. And maybe because there is only one short part, let's finish this before the break. You will have your 10 minutes, don't worry. And then we can start a completely new problem. So this was part 4, starting over here. Finding the time constants. Part 5. If 50 kilograms, if a 50 kilogram lump of coal falls into an empty coal truck, okay, so how big, so the truck is empty and then you have big lump, okay, what steady state deflection in millimeters, which doesn't matter in fact, eventually appears on the linear pointer scale, eventually. So now we know there will be a transient process, but eventually really means what? Steady state value. So what is the steady state value, in other words? Eventually. Okay. So we want to see what is the steady state value of the output, which is y, if the input is described here as it is. So how do we mathematically describe what is happening here? Our 50 kilograms of coal falls into a truck, empty truck, an empty wagon. What kind of function is that? It is a step, but is it really a unit step? It is 50, step of magnitude 50. You're all happy to agree that this is a step function because you have an empty truck, so the input is 0. And then suddenly you get 50 kilograms. So you have an input jumping to 50 and staying at 50. Okay. It's not an impulse. It doesn't bounce out. Okay. It's cold. It's not a basketball. It's cold. It just drops there and stays there. Okay. So it is a step. So the steady state value, y of infinity, is equal to limit. Okay, do we have equations? Well, this is not an exam paper, but you will have this equation. So limit when s approaching 0. Why am I using this equation? because if I do that, I don't have to find the inverse Laplace transform. I don't have to find y of t and make time equal to infinity to find what the steady state value is. So actually, the whole problem, as complex as it looks, doesn't require you to do inverse Laplace transforms, possibly partial fractions, using the tables and getting the output in the time domain. So just limit of what? Of s times y of s, which is equal to limit s approaching 0 of s times input times transfer function. That's what output is. So we already said 50 over s times the whole transfer function that we had before. G mu, so I'm making this leg really long, A alpha over K2 ML S squared plus CM plus K1 over M, brackets, brackets, R over L plus S. Okay? Okay, so then we cancel S and S. S is missing here as well. Okay, S, CS over M. So this becomes equal to 50 G mu A alpha over K2 K2. Now we are going to lose ML and M. Okay. Because when S is approaching 0, this is 0, this is 0, and this is 0. So we have R over L, but L will be cancelled. We have K1 over M, M will be cancelled. So it will be K1, K2, K1, R. Once again, you need to substitute the values given here. Beware of the units. And according to my calculations, you get 0.245 meters, or since the question insists, it's 245 millimeters. Okay, any questions? If not, enjoy your well-deserved break, 10 minutes, slightly less than that, maybe, because we have more things to do. 8 minutes. Yeah. Hi.
So when you're trying to find your time constants, does your coefficient in front of S always have to be just 1?
No, no. Your coefficient. Sorry. Your coefficient in S to the power of 0 has to be 1. Okay, so what I did here, a bit clumsily, is I created this to be 1 and this to be 1. Then whatever multiplies S is the time constant.
Okay.
With the first order system.
Isn't it the reciprocal of that?
No, it's L over R.
Oh, it is?
But it's reciprocal of R over L. So when it is in the normalized form, it is the reciprocal of this. Or non-dimensional, it's actually there.
That makes sense, yeah. I'm just wondering what would happen for the second order system if your you didn't have a double loop.
Then you have two time constants.
And what does that mean?
In a system means, okay, then that means that the longer time constant dominates the response.
Right.
That means that you have one exponential like this and the other one like this.
Yep.
So this one is longer time constant, e to the minus, I don't know, t over 100.
Yep.
And this is e to the minus t over 2.
Yep.
Okay. So after a while, this one, the shorter time constant, disappears. But the longer one is still there. Sorry?
This is like, you can treat this as a transit system, yeah?
Yeah,
This is
but,
DC gain.
but you're actually adding these two. In the response, if you have two, like this, sorry, adding, you are subtracting, but anyway, this one disappears. One will disappear quicker, so the other one is staying there. So it is the longer one that dominates the response. The slowest time constant, if you have 5, it is always the slowest one that dominates the response.
Right.
So the system is as quick as the slowest part of the system.
Yeah. Okay.
So in our system, in this system, we know that electrical is much quicker than mechanical.
Yeah.
So the whole, how quickly the pointer settles depends on these time constants, not this one.
Yeah. Okay. Okay. Thank you.
So I just want to ask about SPM.
Yeah.
So I just realized if the, for example, the root come across like this way, the damping ratio will be negative. And in this point, damping ratio will be 0. But along this way,
Yeah.
damping ratio will be greater than
1.
1, yeah?
That's right.
So if the question asks like,
Okay. This point here is a very tricky point.
yeah, the
Okay.
neutral state.
Yeah, but it's not the neutral stability, it's also the origin of the...
Yeah.
Okay, this is actually, damping ratio will be less than -1 over here.
Yeah, but if
Which
the
is,
if the person asks like the stable system,
Yeah.
do we need to include a neutral?
Is 0 considered stable, or
Yeah.
is that
Zero,
considered
zero
largely
is neutral,
stable?
neutral stability.
Yeah, because
So this is
for example,
neutral stable.
they give the like just function, and they give the characteristic
Okay,
equation
you have-
like
yes.
SMS, for example, to damping ratio.
Yeah.
Yes,
Yeah.
But when the question asked like derive the what's the
Stability.
Yeah, stability.
This is neutrally stable, because if you have a pole here,
Yeah.
then the system is neutrally stable.
Okay, so do we include that in
Yeah,
our
do we
bound
need to include that?
stability?
Yeah.
Basically, is it a strict limit or is it
Sorry.
Because like, if you set k to 0.5, you end up with a 0 pole. Is that considered stable or is that not
Sorry,
stable?
is this S here?
The question
No.
was, what
so
value
this is
of
like
k,
a constant coefficient.
what
is
values
a
of k makes it
constant,
stable?
No.
No.
S is the very, so this is the
Because all
S
you need
length.
is, for example, the root is 2a minus b plus. Yeah. So if this discriminant is less than less,
No, that's
Is that
right.
less than
But
or less
this,
than
so
right?
is this constant? There's no brackets here. So it's a constant times S squared, right?
Yeah.
Then you just divide by this constant. So actually, this is not your omega n squared.
Yeah.
Omega n squared will be this divided by this.
Yeah. But this is just like a
Yeah. But this doesn't bring your root here.
I
It
understand.
doesn't
But
give a root here. What I thought you were asking is that if you have S and then some, S blah blah blah.
Yeah.
So you have S and K up
Yeah, that's it.
Now,
Is that
is this
stable?
system stable or not? It is neutrally stable.
So do we consider that as stable or unstable?
It is
Stable.
neutrally stable.
So it's not
still
either. It's
stable.
just-
Yeah,
That's called neutrally stable.
Okay,
Neutrally.
neutrally.
N-E-U,
yeah, but so
neutral.
we still need to conclude that case.
Would you say that if the question said for what values of the question was, you could basically vary k, and then
Yeah.
how you vary k depended what poles you got. So if you had a value of k,
Guys, that's what we do next week.
Well, this
next
is
week.
this is the lecture 9
yeah, that was in lecture. That was in
Lecture
lecture.
9.
content.
Basically, the question is, if I choose a value of the parameter that gives me a pole at 0, is that a valid value to give it a stable
No,
case?
what you're talking about is if you have here k over something. Okay?
Yeah, where-
And then you apply a negative feedback loop. That's the correct. Then k, the new system will have k in the denominator. So now k
Yeah, that's
affects
right.
the poles of the closed loop system.
Exactly, yeah.
That won't be in the test.
Okay.
That won't be in this test. It will become more clear after we do the root work. So next Tuesday, rather than this Friday. So at this stage, I'm happy you're asking that, but it's not relevant at this stage.
From
question 4 on the tutorial, where basically it was a first order undamped system, and you get.
Tutorial is that okay? No, that's okay. I'm just looking for what is
It
called.
doesn't have it's tutorial set 5. Sorry.
Set 5.
Number
Oh,
4.
set 5. Okay.
This one
Right.
here.
Yeah.
So it's
It's a first order system.
yeah, but when you got the inverses and everything, you come out with a sine, a cos,
Yes.
and an exponential. We
Yeah.
have to know the trig rules to form that into one, or do we have to?
Well, okay. Let me tell you this. If you don't know the rules, there will be enough. If you get a problem like this in the exam, there will be enough help to get you from here to
the
here
phase
without spending half an hour. You know, in an exam, the last hour and a half. That was the took through.
So in this case, why M is not equal to W? Is this because W is much less than the M? Yeah, because you said that at the beginning,
Yeah.
the mass is
Much smaller.
So we consider the M is constant.
Yes. But that's a very good point. Then after a while, M, you can't say M is constant.
Yeah.
That's right.
That's right. But
That's
in
right.
this
So-
case, we assume M is constant.
That's right. And all further questions actually don't contradict that assumption. That is actually very important. Very good point. Very good point.
And the last question is, the beginning of the lecture, you said that this phi is raised.
No, it is. Psi is.
Psi.
It's psi that is 0.5. No, the number I gave you last week was psi squared. I forgot to.
Yeah, that
find
makes
it
sense.
where- Yes, okay. Okay.
So in this week's tube,
Before I mix up. Okay. Yeah.
in this week's tube, this question it was just saying give you the poles and it said about the transfer function.
Yeah.
But it says the DC gain is K, and then in the solution, it's written in a normalized form. That's not the same DC gain though, is it? Because you need to
That's
divide.
correct. Sorry,
Is there a different kind of gain, or is it?
Okay. Let's see.
Yeah, that one.
Okay. All right. Yeah. You're right.
I just thought I
Okay.
thought
That's
maybe-
K1. That's K1. But
K1.
just one is invisible. It's K1. Or this is K1. Yeah.
Earlier in the class paper, just filling out that block diagram, why did this one on MC?
Oh, okay. This problem where it's somewhere hidden here. Okay.
Yeah, I have to.
Because here we have what we had as an equation of Q in minus Q out is the rate of change of internal heat. Let's just call it Q. Now this is rho V C T dot. But instead of rho V we have M. Okay. Heat in is what comes from the friction. So it's mu F V and capital H. I think there's a conversion factor. And this is Q out. That's H A T block. Sorry, yeah, theta block minus theta A. Okay. So now, if you have F here, F is multiplied by mu VH. Okay. So that's what you have. This whole expression is what you have on this line. On this line, you have this expression. Our theta B minus theta A is simply theta. Okay. So theta times HA gives you this that comes with a negative sign.
Okay, so is heat lost, is that always going to be represented by a negative feedback?
Well, in this case, yes, because this is what. This equation is this summation here. Okay, so this is the result of the summation. So you have two components, positive and negative. Okay, how do you create this negative? Well, you need theta, which already exists. So you multiply theta with this constant. So you take theta multiplied with this constant to get this expression over into the summation. And then the result is MC theta, not T, it's theta dot. Okay, so you already have theta dot, and so this is MC theta dot, this is theta dot. So you need to divide by MC. Okay. Yeah.
again a simple question about how to get this equation.
Okay.
Yeah, I look at the choices.
Yeah. No. You have to. What you need to do is do partial fractions here. And one of the guys before, a few minutes ago, he asked the same question. When he did the partial fraction, so he got the exponential term, he got the sine term, and the cosine term. Okay.
Okay, so
Then from there, joining the sine and cosine together, you need to be very good in trigonometry. You have to be, you need to know the rules. If you don't know the rules, it will take a long time, maybe half of your exam time to get from exponential plus sine plus cosine into exponential plus cosine with a shift. So if you get a problem like this in the exam, if you get a problem, you will get a lot of help. So don't spend too much time getting this particular expression.
Are we going to be able? Are we going to be asked to derive that equation?
Sorry?
Are we going to be asked in the exam to derive that if we need it?
Well, that's what I said. If you are asked to derive that, there will be a lot of hints.
Okay.
So you don't spend too much time deriving.
Okay. Yeah.
Okay. A lot of help. Or maybe the other way around. Maybe I'll ask you to show that this will happen. Or I will say, well, if this is the output, then sketch the response or something. Sketch it or something of this. Well, there will be questions that don't require you to spend half an hour getting here. That's ridiculous. That's not what I'm testing.
Yep.
Okay. So you either won't have a question like this or will have a lot of help to get to this expression.
Okay. Yep.
so just to understand this thing, you want to show the questions in the exam?
No. If I am not saying this will be or won't be in the exam. I'm just saying if this is in the exam, you will be given a lot of help in the text of the question. You will be given help in the exam to get to this point.
The instructions.
Instructions, yes.
Okay.
Yes.
Okay, thank you.
Okay, maybe we should continue now. Where are we?
Okay, problem 9. You can try to find it. I will also try to find it. Where is it? Okay. I'll just keep these. Okay. So you have a water tank system. You have two tanks. You have an input flow, you have the output flow, and you have two heights defined as the variables. Okay. So first, you're asked to draw a block diagram, which is actually very fitting. I didn't plan this, but I promise there will be a block diagram in the mid-semester test. So let's do some practice here. Practicing a block diagram of a water tank system. We did a similar example, very similar, apart from I think the input was here, not here. Very similar example in lecture. So let's have a closer look at this system. We have two tanks and two valves. So let's write equations for each tank and each valve. So for the first tank, the equation we want to write so this is question 9. Tank 1, we have Qi minus, we're going to call this Q1 temporarily, minus Q1. So all flows into tank is Qi, all flows out of the tank is this Q1. Will result in a rate of change of volume in the tank. Now since area A is constant, it's A times H1 dot. That's equation 1. Tank 2. Identify the flows in. It's this Q1. Minus flows out. There's only one flow out, and that's QO. That results in A is the same area, A H2 dot. Flow through the valve 1, which is Q1, is equal to the height difference, H1 minus H2, divided by R1. Flow through the second valve, there's only H2, nothing on the other side, so QO equals to H2 over R2. Okay, so we want to draw a block diagram using these 4 pieces of information, these 4 equations. As we said so many times so far, if this is the input and H2 is the output, we need to put everything else in between. If we want to start from the left, Qi exists in equation 1. So let's create equation 1 here. Let's draw a part of the block diagram that corresponds to the equation 1. So we are going to have some sort of summation, Qi minus Q1. Okay, it's not for me, I'll try to ignore it. Qi minus Q1 equals to, I'll just write this here, AH1 dot. Okay. We'll see later how we get this Q1. But we know we are going to need H1 at some point later on. So let's create H1 out of this. So first, we are going to divide by A. And then we are going to integrate H1. So this is H1 dot. And when we integrate that, we are getting H. H1, rather. You're getting H1. That's still equation 1. Now, we still have this problem Q1, but we don't have it created as yet. So we'll leave this as it is. However, equation 3 will solve that problem. We'll get Q1, but we need to subtract H2 from H1. We already have H1, and we know, or at least we hope, we'll have H2 eventually. So we take H2 with the negative sign, which will give us the difference between 2 gives us R1 Q1. So we need to divide by R1. Okay, so this is Q1, something that we can take back. I don't think I left enough room here, so that's going to be a little bit of a problem. Now, equation 2, Q1 minus QO will give us a H2 dot. So I need to somehow create Q2 here. Okay, with the negative sign. That now becomes equation 2. And that gives me a H2 double dot. since I didn't do a good planning, I'm going to divide by A and integrate at the same time in order to get H2. But just to clarify, what I have here is A H2 dot. So I'm dividing by A and integrating, so I'm getting H2. Sorry? Q2, well, that's something to, still left to be resolved. So sorry, Q2, QO. Right, Q1 minus QO. Oh, okay, okay. QO, thank you. So Q1 minus QO gives me AH2 dot. And then I divide by A, and then I integrate to get H2.
Attention. This is the Chief Warden. An evacuation exercise is about to commence. I repeat, an evacuation exercise is about to commence. On hearing the alert tone, can all wardens please report to the whip phones? All other occupants, please remain in your current location and await further instructions.
Okay. So I'm happier that you do it now than on Thursday. That's the tone. We have to evacuate. Sorry, guys. Okay.
This campus is being evacuated.
Campus. Okay. If we get back before, if we finish everything by...
This building is being evacuated.
Building, okay. Okay, okay. If this is done before 4, please come here. We can continue.
Are you able to upload answers to the past mid set? Specifically for question 1? No?
No. You have a solution to the quiz from this year, which is the same problem. So just look at the solution.
Oh, okay. All right.
Excuse me, sir.
Yeah.
I'm just wondering, when you do the block diagram, can we just initially like the Laplace into the S domain?
Oh, yeah.
Then, because you are working in the time domain, yeah?
Yeah. It's just I'm writing in time domain, but my transfer functions are in the S domain.
Mr. Lecturer, you have to leave as well.
No, I'm leaving. I just have to close everything.
Evacuate now.
Yeah.
Are you going to continue?
Emergency.
Sorry.
Are you
Evacuate
going to
now.
continue?
I don't know. I mean, if they let us in before 4, we'll continue.
Emergency.
Outside my control.
Evacuate now. Emergency. 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 Evacuate now.
Attention, attention. That concludes the evacuation exercise. I repeat, that concludes the evacuation exercise. Please treat all further alarms as real. I repeat, please treat all further alarms as real. Thank you for your cooperation in this exercise.
I'm not staying back to 8. I finished 5. Just do it.
No, I think the system. No, what are you doing? What are you doing? You realize this is being recorded?
Free advertisement.
There were other people with vests without markers, right? Yeah, yeah.
You're asking for it.
a natural monopoly. It's not. It's. Wait, Justin, sing up. Leo, go. Try.
Okay. You're not using the computer anymore? No. Okay. Okay. Thank you. All right, I hope you're all safe now. Okay, this is a bit too loud. What do you say? We have the block diagram of our system. Now, next thing is reduce the block diagram to obtain the transfer function relating Qi to H2. Okay, so we are applying the rules for the block diagram reduction. Oh, sorry, we haven't finished the block diagram. Beg your pardon. QO
Now, where are my equations? My equations are here. So we still have QO to create from somewhere. And on the other hand, there is still equation 4 we haven't used. So you see that QO is equal to H2 over R2. We already have H2. So all we need to do is divide by R2. So if you take H2 and divide it by R2, that will be equal to QO. So this completes the block diagram. Okay. Any questions, or should we move to the reduction part of the block diagram? First thing, I think the only obvious thing is this negative feedback loop. And also we have this series configuration as well. So we can multiply these two and also resolve this negative feedback loop. That takes us to Qi. 1 over AS (1 over R1). Now here, this is G1, this is G2. So it's 1 over AS over 1 plus 1 over ARS. H2 over here. And here we have this thing. Q1. This part, let's just simplify that. So that will be 1 over, no, it will be R2. No, there is no R2, sorry. There will be R, just R. ARS plus 1. There's no R. Sorry, yeah, there is R2. My mistake, sorry. R2 missing here. So it is R2 and it is R2. Yeah, trying to make up for the missed time. Okay, so this is now simplified. At this point, there is nothing clearly easy to do, the thing that is clearly easy to do. So we have to apply one of those rules where we are moving one of the junctions to a point where we find it most convenient. So we either move this point back here, or we move this point over here. Okay, no, moving this point will not help us. So the only way to continue is to move this part over here. So that will give us Qi 1 over AS (1 over R1) R2 over AR2S plus 1 H2. Here we have minus. And now here we have AR2S plus 1 over R2. Okay. Because we still want this signal to be Q1 here. So what we did by moving this junction downstream, we actually multiplied Q1 with what's in the box. Now we need to divide by what's in this box to get back to Q1. Okay. Now we have a couple of feedback loops to solve, and obviously one multiplication here. So Qi summation 1 over AS. A feedback loop here, the main loop contains these two, so it's this times this. The feedback loop, the feedback branch, it's 1. Okay. Transfer function in the feedback branch is 1. This is, so G1 and G2 is not what is on top, what is on bottom, but actually what is in the main line, in main branch, and what is in the feedback branch. So this becomes R2 over R1 A R2S plus 1 over 1 plus the same thing. R1A R2S plus 1. H2. Here it is A R2 S plus 1 over R2 minus, oops, can you see this? Now this, when simplified, becomes R2 over R2 brackets A, it's not R2, R1, R1 brackets A R2S plus 1 and plus R2. Multiply this with this, and then your last feedback loop. Qi, a big box, R2 over A squared R1 R2 S squared plus A R1 plus 2 A R2 S plus 1 H2 as the output. Okay, so I'm skipping, obviously, a step or two here. Right. So having done this, now we have our transfer function. We can answer a few more questions, 3 more questions. So question 1, okay, no, obtain the time constants, okay, of the time domain solution. That is, look for the roots of the S in the characteristic equation. So here we have 1. This is a non-dimensional form. If you want to factorize this, we need to find S, which will be equal to minus AR1 plus 2AR2. So we are looking for the roots. Plus minus square root of AR1 plus 2AR2 squared minus 4 A squared R1 R2. And all that divided by 2 A squared R1 R2. That's it. So this is S1, S2. 2 roots. So let's call them, we need to find nice letters, M and M, capital M, capital N. So we can rewrite the transfer function as R2 over S minus M, S minus N. If these are plus M and plus M. But because we want a non-dimensional form, so it's R2 over M N, S over M plus 1, sorry, minus 1, S over N